What's going on, everybody? It's Mr. Diamond, and here we have our second example of an inelastic collision. This one is specifically called a ballistic pendulum. So what's going to happen here is we're going to have a bullet, and I'm worried that I'm going to forget what that mass is really quick, so I'm going to rewrite it. We have a bullet that weighs 0.15 kilograms, and it's being fired at a velocity of 240 meters per second. But instead of it being fired into a block and just passing through, or being fired into a block and embedding in it and like going flying off of the table or off of wherever it's at, we have it suspended by a string. And the length of the string is kind of irrelevant for our purposes. We're going to assume that it's like an infinitely long but also massless string. It's just literally there's a string going up to whatever you believe is out in space, attached to something, somehow vertically suspended, so that if it gets hit, it will swing backwards. So when it gets hit, instead of it sliding straight back, it's actually going to arc back, and it's going to swing backwards this direction. The block, so mass of, I guess bullet is bad, so we're going to say mass of wood. The wooden block is going to be 10 kilograms. And the question asks not anything about the velocity, not anything about any other of the weird components of what we're talking about. The question's asking how high will the block swing back? Which seems like a really weird question. Like that doesn't really immediately seem like there's like an obvious way to figure out what's gonna be happening here. But we do actually have a way to solve for it. So first thing that we're gonna do, we cannot use VA1 plus VA2 equals VB1 plus VB2. The reason we can't use that is this is an inelastic collision. Now, the question doesn't explicitly tell you that it's inelastic. You know that it is because we're in the example section where we're doing inelastic questions. But it doesn't explicitly come out and say, oh yeah, this is an inelastic collision. So you have to be able to figure that out. Hopefully, it makes sense like by looking at this why this is an inelastic collision. Inelastic collisions are where things usually lose energy or they stick together whenever they're hit. They deform, they go through some other change. And in this case, this bullet is lodging into the block. And because it's going to lodge into the block, that means that it's going to be perfectly inelastic collision. They are going to completely embed itself into that block, and that means that we do not get to have kinetic energy conserved, which means we do not get to use our VA1 plus VA2 equals VB1 plus VB2 equation. So what are we stuck with, or what are we left with? We are left with momentum is conserved, and that's about it. We have to kind of figure out what's going on here with momentum. So we can figure out momentum 1. Our momentum 1 is going to be the momentum of the wood plus the momentum of the bullet, but we know that the wood is stationary, so it's going to go away and that's going to be canceled. So our initial momentum that's being put in the system, PB, is going to be 0.15 kilograms times 240 meters per second. I worked this out earlier. I don't actually have my cheat sheet, so if I make a mistake in this, I apologize. I'll try not to, as if I would ever try to make a mistake. 15.15 times 240, we get 36. So 36, and that is kilograms per meter seconds. So that's our momentum at state 1. At state 2, which is going to have to be equal to P1, which we just solved was 36. We know that there's really only the block bullet system. So our mass in that case is going to be the mass of the bullet, which is 0.15 kilograms, plus the mass of the block, which is 10 kilograms. And then that's going to be times the V at state 2, the velocity of the bullet block system. We can solve that pretty easily. V2 is going to equal 36 divided by 10.15. 10 plus 0.15, didn't need the calculator for that one. We get that it's going to be traveling at a velocity of 3.54679803, which is a velocity of we'll say 3.55 meters per second. Okay, we've done equations like this. There was questions that asked about like when you hit the block, like what speed is it going? But this doesn't obviously seem like where we should have been going in the problem. Like this isn't really like super obviously where we were trying to go. What I'm assuming, and the reason I solved this far, is because I assumed most of you would have just done this by natural instinct, not because of an understanding of what the problem is asking, but because you'd go, well, I know that this is an equation, I can solve for this. Okay, cool. I know what the velocity is, the second part. But what does that matter? So we know mass at position 2, and we know that the velocity at position 2. So mass is 10.15, and our velocity is 3.55. That's kilograms, that's meters per second. And then I assume a lot of you would probably get stuck from here. It's not super obvious what our next step is. And here is where we have to pull in some things from last chapter. Just because kinetic energy is not conserved does not mean that kinetic energy is useful. Because when this block swings, it is going to go through some amount of change. And notice that we're trying to find a height here. Where in the past have we talked about heights in relationship to energies? Well, we actually know that potential energy is equal to the mass times gravity times the height that an object has been displaced. And we're trying to solve for a height in this problem. That's what the question's actually asking us about. But we don't have any information about potential energy, except that energy also has to be conserved. So E1 equals E2, which means that we can actually think of a second set of states going into this reaction, or going into this equation. So what I'm going to do is I'm going to scoot down the page, and we're now going to, we figured out information about the whole, while it's swinging, it's going to initially move at 3.55 meters per second. Let's now think about, I've got my block that's suspended, that has grown in size. At this exact moment, when it's hit, when the bullet hits it, that is when it's going to be moving at 3.55 meters per second. But because it's attached to this string, it's going to swing at an upward slope. It's going to move upwards some amount. Let's just pretend that it moves up that amount that I have right there. So at position 2, after it's been hit, you're going to have, your box is going to be over here kind of horizontal. It's going to be tilted up. It's going to have gone up some amount here. But what would its speed be once it hits the highest point of its swing? Well, its speed would be 0 meters per second, which means, pulling all this together, and I know some of you may not have thought of this directly while doing this process, but this is the proof of where it's going to come from. We can actually use KE1 plus PE1 equals KE2 plus PE2. That the energy at the two states are going to have to be the same. So for our state 1 for kinetic energy, we're putting in 3.55 meters per second at this speed. And for potential energy, we're going to assume where it's currently sitting is 0, which means our potential energy is going to go away. Once it swings up, it's not moving anymore, so our kinetic energy is going to go away, and we're left with only a potential energy. And that is how we can use that speed to finally solve for height. We can plug in that KE1, which is 1/2 mv squared, equals PE2, which is mgh. So I've got 1/2 mv squared equals mgh. Notice that mass disappears, but I'm going to leave it in just because I assumed most of you would leave it in, at least at the first part. Maybe you'd cancel it. I don't know. So we have 1/2. Mass is going to stay the same. We have 10.15 kilograms. Velocity is going to be 3.55 meters per second. That's going to be squared. Equals mass is 10.15. But again, we're going to cancel that. We're not actually going to plug that in. G is 9.8. And then height is going to be our unknown. Plugging all of that in, canceling the 10.5 so I can get rid of that, I get 3.55 squared to get rid of this altogether. I'm going to times that by 0.5 to again get rid of the 1/2. I'm going to divide that by 9.8, And I get that after it gets hit, it will rise a total of 0.64298, or if we round it, 0.643 meters. It will rise up 0.634 meters after it has been shot. So the question starts kind of weird, and it's a little bit difficult to figure out where it's going, but we can connect things from last chapter to actually solve this really interesting physics problem. All right, that's what I've got for this video. If you got any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.